The substitution method is basically here we simply making a good guess of the solution, like we are given a recurrence relation, like suppose this is the recurrence relation. So before finding the upper bound, we simply guess like this can be the solution for this recurrence relation, and after guessing that, we will prove that the guessed solution is correct using the mathematical induction and the boundary or initial condition. Okay, so there is a term like initial condition, okay, and the boundary condition. So these both are the same. Initial condition or boundary condition are those. These are related with the base case. Base case for that particular recurrence relation. Base case means like t of 1 or t of 0, the values of t of 1 and t of 0. Like we are solving the problem of factorial. We can draw a recurrence relation for the factorial. And in the base case, the value of t of 1 and t of 0 in the factorial. Same like the Fibonacci series. So if we are given a recurrence, then there must be a base case. Means in that after that the problem cannot be divided or decomposed or reduced. Okay, and we know the value of the base case that can be used to find out the solution. So in the recurrence relation, we simply make a good guess the form of the answer, then use the induction hypothesis to find the constants and show that the solution works. So in the mathematical induction or induction hypothesis, we simply prove or guess the solution on smaller values of n, and after that we prove that for larger value of n, and then we'll find out the constant values according to the bound, like if we are finding the lower bound or upper bound. So this is an example, like suppose we are given t of n equal to t n by 2 plus theta of n. So it is a typical method as there is a problem to guess the solution. I know the solution of this function or recurrence relation t of n equal to t n by 2 plus theta of n. The bound for this can be t of n equal theta of n log n. Why? Because this is the recurrence relation for merge sort. So in the case of merge sort, the time complexity is in the order of n log n. But suppose we are given this function for this recurrence relation t of n equal to t n by 2, this is the floor function here plus n. Then what can be the solution? In this case also the solution will be like this, because there is a little impact of the floor and ceiling function on the solution. The solution for this will be like the theta of n log n. For this one, we don't know. We will solve that. It is a constant value, and what can be the solution? We will guess the solution. So the problem in the substitution method is one, like we need to guess the solution, and suppose we are unable to guess the solution, then we will not be able to solve the recurrence relation by the substitution method. So guess the form of the solution, then use the mathematical induction to find the constants and show that the solution works. So the substitution method can be used to establish either upper or lower bound on the recurrence. Means after giving a recurrence, we can be asked to find out the lower bound as well or the upper bound on that particular recurrence relation. So let's have some questions in numerical so that we can understand the whole logic. For the following recurrence relation, find the upper bound. So this is the recurrence relation, t of n equal to t n by 2 plus n. So it is same that we have discussed previously in the previous slide. It is the recurrence relation for merge sort algorithm. Okay, and this is the base case. And we'll show you some important thing at the end of this numerical about the base case. So in the first step of this method, we simply need to guess the solution, and we are defining the upper bound here. So assume it like the solution is t of n equal order of n log n. For the upper bound, we will use the big O notation. Now when we have guessed the solution, then now we need to prove it. So initially, what we need to prove it? It is the upper bound. So as per the big O notation, Tn will be less than equal Cn log n for C greater than 0 and some constant and not. Okay. So by induction, let's assume that the bound holds for n by 2. अब ये इसको हमने क्यों चूज किया? The simplest answer is this: it is present in the recurrence relation. तो जिस स्मॉलर इनपुट के लिए हम प्रूव करेंगे, just pick up that from the recurrence relation if we can. Okay, let's suppose यहाँ पे होता है 2t(n minus 1), then we will prove that for n minus 1 in smaller value of n. Let's suppose it is 2t(n by 4), then we will take that n by 4. We will find out or prove that by assuming like it is holds for n by 2. So t, we are given the recurrence relation t of n. We will remove this ceiling function here. T of n equal to tn by 2 plus n. Now, which value we can replace in this recurrence relation? This one, tn by 2. So we will find out the value of tn by 2 from here, as t of n equals cn log n. So t of n by 2 will be cn by 2 log n by 2. So we can put this value here. It will be 2cn by 2 log n by 2 plus n. Now just solve this. So it will be t of n equals cn log n by 2 plus n, or it is log m by n. So it will be log m minus log n. So it will be cn log n minus cn log 2 plus it is n. So we can assume here in maximum cases like the base will be 2 whenever we are solving such type of equation. So base will be 2, so this log 2 will be 1. It will be, we can simply take cn common, so cn bracket log n minus 1 plus n. It is log n minus 1, or it will be 1. So cn log n minus cn plus n. So for the value of n equal n by 2, we get this value. And this must be less than equal cn log n as per the big O notation. Okay. So now we need to prove that our assumption holds true for the boundary conditions also. This was the assumption. But you can see here for n equal 1, we found that t of 1 equal 1 as we are given in the question initially. So t of 1 equal 1, but for t of 1 it will be for n equal 1 it will be 0, and this will be 1. So 1 less than equal 0, it is not possible. Okay, so this for n equal 1 our boundary conditions are not hold. So what we will do, we simply move the boundary condition from 1 to 2. So boundary conditions for the recurrence is taken as tf2, and we will take that value for c greater than equal to. So tf2 equal 2t log 2 plus 4. It is t of n equal c n log 2. Okay, so it will be 2 into 2. 2 into 2 multiply log 2. The log 2 will be 1, so it will be 4. 2 into 2 will be 4. So for n equal to and c equal to, we get it 4, and the same we will find out the value for this. It will be 4 log 2 minus 4 plus 2, that will be 2, and it is less than 4. So for 2 it is proved. Now for 3 in the same we will check. So for 3, 2 into 3 log 3, and it is a base 2. So log 3 base 2 is 1 point, it is around 1 point something, and we can solve this, and we will get the value of t3 for this. It will be 9.51, and for this the value will be 6.5. So it is also less than 9.51. Okay, so the solution is true for c greater than equal to 2 and n greater than equal to 2. So we can say like our guide solution c of n equal O of n log n, it is whole true. Okay, so this is the method for solving the recurrence relation using the substitution method. So we can understand it by one more example, and we can solve some other examples also. Let's suppose we are given this t of n equal t n by 2 plus 1. So whenever we are solving this, just ignore the floor and ceiling function. We can assume the solution of this. So by viewing it, we can say that it is the recurrence relation for binary search algorithm. But in the question we are given, show that it is asymptotically bounded by O of log n. Means we are given the solution, so there is no need to guess the solution. Just we need to prove it like it is the upper bound of this particular recurrence relation, and by founding the constant and n naught value. So we have to prove that t of n less than equal c log n, where c is greater than 0. Okay, so by induction, let's assume that the bound hold for n by 2. So for this, we will take the value, and so मैंने यहाँ क्या value ली n by 2 smaller value. So I have just told you, just take the smaller input from the recurrence as here n by 2, because that value we only can be able to replace. So for n by 2, it will be t n by 2 less than c log n by 2 from here, and t of n equal t n by 2, it is our main recurrence. We simply put this value here. It will be t of n equal c log n by 2 plus 1, and t of n equal c log n minus c log 2 plus 1. That must be less than equal c log n. So it will be true for the value of c greater than equal to 2 or n greater than equal to 2. Why? If we simply take the value of c equal 1 and c equal 1, it is also 1, then it will be 0, and both functions will always same. So that's why we need to take the value of c greater than equal to 2, means greater than 1. So for c equal to 2 and larger value, it will be true for n greater than equal to. So for c greater than equal to 2 and n greater than equal to 2, t of n is equal O of log n. These are the boundary condition, and these are holds true. Assume this question, we are given a recurrence relation t of n equal 4t n by 2 plus n square. So here also we are given the base conditions, but for solving this, we need to change the base conditions also for this recurrence relation. So let us guess that t of n equal omega of n square log n. This can be the solution for this. And now we need to prove here lower bound. In the case of lower bound, means we need to prove it in omega notation. And as per the omega notation, t of n will be greater than equal c n square log n for some n naught and c. Okay, so now for the inductive step, as we can assume like hypothesis is true for n by 2. Why n by 2? Because it is in here. So we will prove it for n by 2. How? We are given the recurrence relation t of n 4t n by 2 plus n square. So we'll find out the value of t n by 2 from the gas solution. It is c n square by 4 log n, and we can simply put that value here. After putting that value here, we will get this t of n equal 4 c n square by 4 log n by 2 plus n square. And after solving this, 4 will be cancelled out by 4. It will be c n square log n by 2, and we can solve this. And after solving this, we will get t of n equal c n square log n plus 1 minus c n square. And this value must be greater than equal c n square log n. So when this value will be greater, when there will be some kind of addition in this function. So this value must be a positive value. Means the value of c must be less than 1, because when this will be less than 1, then 1 minus that's less than 1 value, there will be a positive value. Okay, so for c less than 1 and n greater than not equal to 2, we need to take that value. And if we simply take for n greater than equal to 2 and c less than 1, it will hold true for c n square log n. So this will be the solution for this, and we have proved this for the boundary conditions also, c less than 1 and n greater than equal to 2. Not Ankit sir? Just a second. Okay. So let's take one more last example, and it is a little typical as compared to the previous questions or examples. Like, there may be some cases when we are unable to guess the solution of the given recurrence relation. Like we are having this one, t of n equal to t root n plus log n. So in this case, we are unable to guess like which type of solution for this particular recurrence relation can be. So what can we do? We simply replace or reduce it in simple terms of n, or in the particular form in which we can guess the solution. So first we simply remove this under root n. So we simply assume like m equal log n. When m equal log n, then n will be 2 raised to power m by the properties of log. Like this, if this is so, then if I want to solve this, then m will be 2 will come in the base and it will be log n. Log base to n, like this. So m will be equal to log n, so n will be 2 raised to power m. And by replacing this value, we'll get t 2 raised to power m equal 2t 2 raised to power m by 2 plus m. Till now it is not simpler, so that we can get a solution. So again, just we can make it more simple. So just rename it like s of m equal t 2 raised to power m. It means we simply want to reduce it from this form, like 2 raised to power m. We want this in the form of m or n. So s of m can be renamed as t 2 raised to power, sorry, this t 2 raised to power m can be renamed as s of m. So as m, it will come here equal to as m by 2 plus m. And now by viewing this recurrence relation, as m equal to s m by 2 plus m, or t of n equal to t n by 2 plus n. So that is the recurrence relation for merge sort algorithm. And we know the solution for the merge sort algorithm, that is O of m log m. So we guess the solution for this transformed recurrence relation. Now we will just make that original recurrence relation, and will convert also this value into the guide solution for the original recurrence relation. So how? We simply replace this value. So replace the value of m. We assume the m here log n. So it will be O of log n log, and the value is log n. So it is log n log log n. तो ये इसके साथ है log log n. So this is the solution, gas solution t of n equal O of log n log log n. Now we will prove this by the induction hypothesis. So as we are just finding the upper bound, then t of n must be less than equal c log n log log n. जो हमने यहाँ solution गैस किया था ये. And now we have, this is the main recurrence relation, t of n equal to t under root n plus log n. So we need to prove it on smaller values of n, and we can take the smaller value from the recurrence itself, like it is n raised to power half. So by induction, let's assume that our bound hold for n raised to power half. Okay, so we'll find out the value of this t of n raised to power half from the gas solution. Here we'll get here t of n by 2 equals c log n raised to power half plus log n raised to power half. And we, for this smaller value of n, means for n raised to power half, we have calculated this value from the gas solution, and we will put this in the ordinal recurrence relation. And after solving this equation, this will be, we will get this, and this must be less than equal to our gas solution. So we need to find out the value of c or n naught, and we have solved some questions in the asymptotic notation. So this will be true for c greater than equal 1 and n greater than equal 1. Okay, so if question, some recurrence relation is given like that we are unable to guess the solution for such type of recurrence relation. And in that case, just try to make simpler that particular recurrence equation so that it will come into a form so that we can guess the solution. Okay, and if we are able to guess the solution, we are not able to guess the solution, then we can use the another method for recurrence relation, that is recursion tree method, that we will discuss later in some lectures. So the recursion tree method is also can be used to find out the solution or guess the solution for the substitution method. Okay, so this is all about the substitution method.